Cool. So is my voice projecting to the back? Funny, weird accent. Yeah. I can push. Yeah, the green light's on. Okay, there we go. I'll just get it a little higher. Leo, I suppose you could just turn the lights down a little bit. Fabulous. Thanks. Cool. So I know that some of you do fMRI today. How many of you would EPI be a string of letters? Does it mean anything to most of you? Okay, so most of you know what EPI is. Okay, good. So is anybody baffled? Anyone not know what EPI is or not know anything about fMRI? Just to sort of get a sense. Okay. So I'm going to try and make this a sort of a teaching seminar. That's the goal. And what I really hope that you take away from this. By the way, I'm going to give the slides to Leon, so don't feel obliged to write everything down. I'll just give the PDF to Leon and he can distribute it. So I don't want you to dwell too much on the specifics because it's just a string of numbers, right? What the TE is, what the number of slices happens to be. You can look that up pretty much. What I'd like you to walk away with today is more of a mental framework, a philosophy for approaching experimental design, because it turns out this is an experiment. And in neuroimaging, too often we sort of abrogate many of the roles to other people, and you would never find that in the physical sciences. If you're a chemist, you specify your own chemicals in your own glassware, and you're expected to do your own work. You don't just then go hire an undergraduate to mix the chemicals for you. So that's the philosophy I'd like you to take away from this, and make sure that you're an integral part of the decision-making process for your experimental design. So before we get into the serious stuff, this is really for Leon. This is what fMRI at Berkeley looked like until June last year. So this building on the left, which is a sort of a weird, funky design, this is what used to house the 4T variant scanner, which is what Leon worked on in the early 2000s. And in 2008, we added this even uglier, plainer box, which housed the 3T Siemens until June of last year. So there's a story behind it. If I have time at the end, perhaps I'll tell you about the story here. But you can tell this is not exactly a traditional building for the Berkeley campus, right? It was a pretty big deal to get these temporary structures on there. So there's the magnet being craned away in May last year, and a short time later it ended up going through an access panel, which is in a walkway, and for Leon again, that is Yali's Cafe, right there on the corner, a Berkeley landmark. By the way, I have your coffee in my bag. And so the basement, which you can't obviously see, is on the ground, the basement, which is about 8,000 square feet, whatever that is in square meters, that is where the new brain imaging center is. So this is all the genetics and cell biology and cancer labs and neuroscience. And we pretty much have the whole basement to ourselves. We have a bunch of space for 3Ts, a 7T bay, which looks like a swimming pool right now. We have a bay for an MEG, etc. But we are 20 million short for the equipment, so right now we have one 3T. We even have posh new facilities, like we have chairs and a waiting area. This is luxury. We have a drinking fountain right here, toilets that you can't see just off to the right. This is just luxury. We never had a toilet. It's just incredible. We even have artwork on the walls. It's just wonderful. So that's what you guys have got to look forward to in, 3 years' time when your new building comes online. Okay, so there's the folly. Let's go back to the science. So here's what we're going to go through today. A bit of background about the strategy, the mens rea, if you will, the way that you should approach the thinking around setting up a new protocol. And then we'll look a little bit at the EPI pulse sequence, and I'll try not to do too much heavy physics. I just want you to sort of learn some of the most important aspects of the EPI sequence. And then we'll get into the concept of having a default. So this is where you should always start from. So this will be your safe zone, right? So think about it as like an island with shark-infested waters around it. And the sharks are actually robots driven by people like me, physicists, who are trying to lure you into the water with the promise of faster methods and everything, but you really want to stay nice and dry on the beach. That's your safe zone. So that's what we're going to talk about, the concept of a default epi protocol. And we can define a default based on basically the limits of the scanner hardware. So anytime you want to move away from the default, you should be asking yourself and your physicist and the literature a lot of questions, because otherwise you should stay on the beach and stay dry. Towards the end, I'll just give you a few generic tips, just from experience about things that you can do to make your fMRI experiments a little bit more successful, no matter what kind of protocol you're using, whether it's a standard default sequence or something that's quite novel. There are many tactics and tips that are quite universal. And then I'll give you a sort of a formulaic approach for asking the questions that will allow you to make an informed decision when you decide to go dip your toe in the water and take a swim in the shark-infested waters around the island. Okay, so here's what you're going to do. The first thing you're going to do is seek lots and lots of input. You're obviously going to want to know the literature very well. You're going to want to talk to your colleagues, physicists here and elsewhere. You want to know an awful lot before you just pick up the latest pulse sequence and start using it blindly. That's a recipe for disaster. One thing that I find most people don't do in fMRI is specify why it is they need, or why they claim they need, what they want in the pulse sequence. They tend to invert the equation, and they say, well, 5 millimeters or 4 millimeters or 3 millimeters, is that good enough? Right? What you should really be saying is, what's the minimum resolution I need in order to define a particular nucleus of interest, or to discriminate between two nuclei that are close in anatomical space? And forget all about fMRI for a second. Just think in terms of just neuroanatomy and Brodmann's areas and the like, and decide what you need to achieve in order to satisfy your experimental goals. That's your starting point, because if you can satisfy those goals with the default protocol, you're done. You just simply take the default protocol and away you go. You go off and do neuroscience and publish sexy papers, and everything is good. You minimized your risk. And you've also just saved yourself a lot of existential angst, because you now don't have to worry about whether the new method is going to create problems for you. If you decide to depart from the default for any reason, then you should make everything a defined, conscious decision. And you should make decisions that are brain-centric, not method-centric. And this is an absolute no-no. You should definitely not listen to people like me, because we will lead you astray. We invent the methods, and therefore we have an agenda. We have a horse in the race, and that's a really bad thing. There's a conflict of interest, right? So you want to be very, very careful whenever somebody's pitching to you that ask a lot of good skeptical questions. I know this is obvious, but how many people have run an fMRI experiment and piloted it in this room? Okay. How many of you have run an fMRI experiment that you didn't pilot? Go on, be honest. One. Okay, 2. That's pretty good. That's a very honourable ratio. There are many people who just simply don't pilot, or they treat the first experiment that goes wrong as the pilot in retrospect. 6 months down the road, they go, oh, okay, I guess I'll change the subjects, change the protocol, change the stimuli, etc. And well, we'll just call it a pilot. There we go. I can justify $30,000 worth of scanning expenses that way. And last but not least, oh, I already mentioned that. Just want to drum that in a little bit. If you don't pilot, you really are not going to be on safe ground. So talking of pilots, there we go. Icon of the day. Some Spitfire that I saw in an air show local to my parents' house. So vision scientists in the audience will yawn at this point, because this is all passé for them. But for most of us, we don't think in terms of conjugate variables or reciprocal variables. But we actually are intimately familiar with common reciprocal variables of space, of time and frequency all the time, right? And these two are seconds and invert seconds. And so we can define a simple relationship between these two with what's known as a Fourier transform. It's just a mathematical formula. We don't need to know anything more than that. And if we know one, we can simply switch backwards and forwards from one to the other by virtue of this Fourier transform. It pushes in either direction. And there's no loss of information or gain of information. You have the equivalent information. It's just represented in a different way, which could be more or less useful to you depending on the particular type of information that you're trying to convey. Okay, so frequencies are very useful for some parameters, and time is very useful for other representations of the same information. The same is true in MRI. So this is MRI in a nutshell. I'm going to show you MRI in basically 2 slides. We need to get this because then we can do a 2-dimensional Fourier transform to get what we want, which is a picture. Right? We want to interpret this stuff. I don't know if you can see the Spitfire in there. I certainly can't. I certainly cannot see any grass. My eye and my brain are not built to decipher K-space. Right? So K-space is simply the reciprocal of real space. That's it. It's just centimeters and 1 over centimeters. Space is centimeters. K-space is 1 over centimeters. And a 2-dimensional Fourier transform is just 2 1-dimensional Fourier transforms applied orthogonal to each other. So the task in fMRI is to get these planes of imaging data as quickly as possible. We want a stack of these that represents the entire brain in about 2 seconds. So we need to fill up this matrix. Once we've got this matrix, we can Fourier transform it. Bingo, we have a quick mathematical relationship to solve, and then we have our picture. Okay? So how do we do that in fMRI? That's the same K-space plane, and this is the sampling we need to do. So there's a rectilinear grid across it. We just need to zip backwards and forwards across it very quickly, sample all the points on this grid. Let's just pretend it's 64 by 64 points. Once we've achieved the sampling of all of these points, we're done. We can then apply a 2-dimensional Fourier transform, and we've got our image of the brain. Okay. This is the sequence that we're going to do it. Everything is color-coded to match. So we're going to do this journey through K-space by virtue of the gradients. And I won't bother to prove this, but basically you can show that the gradient area is a path through the Fourier transform, or path through K-space. Okay? So each one of these colors represents a journey. So we start at the origin of K-space, where we've got 0 information on Kx or Ky. Then we turn 2 gradients on, which takes us in a diagonal direction to one corner of the matrix. And then you can very quickly see that we can zip backwards and forwards by virtue of putting the right colored blips on in the right directions. And we can fill up this K-space matrix. So that's the epi sequence. Well, that's a piece of the epi sequence. This would be repeated for 64 times with 64 little blue triangles if we were doing a 64 squared EPI. So the question that you might want to ask, and maybe you've asked, maybe you haven't asked yourself or your colleagues, is why do we use EPI? Why don't we use something else? Why don't we do DVG or whatever other pulse sequences are out there? The first reason is that this is still, even though it was invented in the very earliest days of MRI, about 1974, and MRI itself was invented in 1971, it's still, pound for pound, the fastest way to get through K-space, and we need speed. Unfortunately, as the need for speed increases, so does the inability of the imaging modality to capture all of the information we want. We tend to be somewhat dependent on, susceptible to artifacts, and we'll maybe talk a little bit about that later on. I'm not going to get too distracted by artifacts today. I'm going to assume that everything is perfect. I'm more interested in looking at the speed issues, the relative speed issues between different pulse sequences. But we do need to recognize that there is also a limit. So if we can go at speed x, why can't we go to speed 2x? Yeah.
Sorry, I'm not sure if it's answer this kind of question, but can you go back a bit and tell what frequencies you're talking about?
The frequencies here?
In the next.
In this one? Okay, well, so first of all, if this is centimeters by centimeters, okay, then this is 1 over centimeters by 1 over centimeters. And that's the same thing. So that is the 1 over centimeters by 1 over centimeters.
So every slide is a different frequency?
Oh, you mean for slide selection?
Every segment of this gradient?
Yes. Oh, well, it's not a different. It's a different K-space position, but it's not. Now, these are actually time domains. So when we look at EPI, when we look at images, we label them with centimeters, right? As far as the scanner is concerned, this is actually hertz by hertz. So this is hertz by hertz, and this is seconds by seconds. So K-space actually is a time domain, and the image domain is actually in frequency space, if you wanted to think about it in those terms. but it's much simpler.
To write just the equation of how you refer to if I may, it's in Cartesian space xy and kx, ky are simply conjugate variables of this without filtering, without windows, without orientation.
Yeah, that's
chosen in the brain.
well.
Some more about that.
How are these chosen? How are these axes chosen?
Yeah.
There are many issues that go into that. Most of them are not user defined. Okay, so on the scanner you get what you get. Okay. Now there are some very simple relationships that govern all of MRI. There's Larmor precession, etc. And you can basically write down a very straightforward equation that you'll find in all of your standard textbooks that will relate these. But that's okay. Yeah, I can. Okay. So okay. This is the parent relationship of all of MRI. Okay, so it says that a frequency is proportional to some constant, which is universal constant, times the magnetic field strength. And what we're going to do is we're going to modulate this with a gradient. So we're going to put, instead of having a flat magnetic field, we're going to just tilt it in one axis. And along that axis, we're going to call this G, let's say G along X. Then we're going to say that omega X is equal to gamma B0 plus the gradient along X. And then what we can do is we can relate a frequency to a position in space. So each point in space is related to a discrete frequency. So that's what's actually happening for each one of these green lines. Each one of these is a readout gradient or a frequency encoding gradient, and they're all actually basically identical. It's being recycled over and over again. And what we're doing is each time we recycle it, we're imparting a slightly different phase. Phase and frequency are essentially the same thing because frequency is rate of change of phase, or phase is the time integral of frequency. So this is another way of building up another representation of frequency or phase in the orthogonal direction. So this is what we're actually building up, but it's really something that during fMRI you probably are never going to think about. What's more useful to you in terms of sort of everyday practice of fMRI is being comfortable with looking at a two-dimensional representation of a K-plane and saying, right, I need to fill this plane. I need to fill it as efficiently as possible, as quickly as possible, and there are tricks that we can play where we can skip parts, and we can there are ways that we can accelerate even from the speed that we've got intrinsic in EPI.
I mean, what's the specific measurement you're talking about?
What's the measurement? Okay, so those little signal, these little things, yeah. So this up here, these little tiny guys here, those are voltages basically being picked up in a receiver coil. So you actually generate, when you put the subject in the magnet, you're polarizing them. You're creating a magnetization, right? So they go from not being a bar magnet to being a very weak magnet. You're magnetizing all the water in their body. And you're then using that magnetization as it's processing around to generate a voltage in a pickup coil. That's the head coil that you put your subject into. Each one of these is, so in this case we pulse megawatts kilowatts of power. So we have a transmit field that puts in kilowatts, and then we receive milliwatts. So these are very, very tiny voltages, very weak signals that are picked up in the sensitive electronics. And it's basically just a very weak magnetometer. It's a copper coil that's sensitive to changing magnetic fields. Okay, so it just oscillates about. So this is all of the information. This is the entire signal from the brain, or from the entire slice in this case, and we've got to unsort all of these signals. These white signals in 2D here are shown in a plan view. So if we sliced through these and tilted them on their sides by 90 degrees, then we would see this kind of view of the signal. So that's what we're measuring. So this is now you can see this is a time axis. We measure signal after signal after signal, and now we can see that the K-space plane is actually a time plane. But we don't really need to think of it that way. In fact, this is why I like to try to start here. If you read the traditional textbooks, they don't introduce K-space until page 50 or page 100. And I think that that's a mistake. I think that this is a useful practical tool. And looking at a lot of the quantum mechanics and a lot of this is not something you do it once. You do it when you write the introductory chapter to your thesis, and then you put it away, and you don't never refer to that again. These are not practical tools. So this is a much more practical everyday tool for thinking about fast imaging experiments. In fact, all pulse sequences, but in particular, fast imaging sequences. So if you ever go to an MRI physics conference, you'll pretty much see nothing but case-based planes. That's how physicists talk to each other. That's how they draw on the back of napkins and represent what their latest idea is. And it's amazing to me that you can still come up with new ways to fill up a matrix, even after 30 years of working in the field. So
It's possible, but I have the feeling that you assume too much physics knowledge.
Well, we're going to get past the physics pretty quickly, I hope. And I'm hoping to talk more about the options that you have on your scanner. So I'm assuming that some of you are going to be doing fMRI if you're not already, and you want to know how to get the best out of the Skyra, which I haven't actually seen yet. I haven't seen a Skyra. I've heard something about them, so I have a loose appreciation of what they can do, but we'll see. So EPI is still the fastest way to cover the full case-based plane. And we have our artifacts that I've mentioned and our limits. So that's an interesting question to look at too. Well, let me do it. I'll come back to this. What are the limits? What defines the limits? Why can't we go twice as fast by just simply turning up the dial? What stops the scanner from going any faster? Well, it actually turns out that there are two very important limits, and they interact with each other. There are biological limits and there are hardware limits. In the biological domain, the biggest problem we have is that we don't want to generate large currents in the heart because it can cause fibrillation, and that can cause discomfort and even death. So, which is obviously not ideal. You wouldn't get that past your ethics committee. So this is the rate of change of magnetic field, dB/dt. That's the rate at which we're switching this gradient on and off. And there is a relatively well-defined limit that as long as we stay below that, then we're not going to cause problems for cardiac fibrillation, which means that we're not going to cause any problems. We're not going to kill anybody. Now, above that limit, and around about the limit of where you're operating the scanner, there can still be issues with peripheral nerve stimulation, because peripheral nerves will stimulate at often even as little as 1/50th of the limit of cardiac stimulation. So it's hard to stimulate the heart. It's quite easy to stimulate nerves that are peripheral, especially large muscles like in your back, etc. Or if you're close to the bore, maybe in your hands, or twitches in your eye. So all of these are not things that you want in fMRI for obvious reasons, I would hope. You want your subjects paying attention to the task, not being distracted by twitching in their eyes or whatever it is. So in any case, we have a biological limit that's defined essentially by law. And that's the hard speed limit that's set into your scanner. So you may not go faster than that. Above that limit, if we were able to somehow shield the heart, then we could actually go slightly faster in the hardware. And then if we look at the physical limits, we're basically looking at putting a lot of electrical energy into a gradient coil, which is what makes the banging noise. And we've got to get that spurious energy out, the extra energy out. So cooling becomes a determining step for how fast we can go. There are also physical restrictions in pulsing these things. We're basically it's a giant speaker. We're putting a large electrical current into a large magnet, and that generates movement. So we have to worry about mechanical resonances, and we have to worry about the loud acoustic noises, and we also have to worry about the forces on the gradient coil itself, which is really just trying to rip itself apart. Okay, so we could go a little bit faster, but at some point the physics of the situation will start to cause the scanner to fall apart, or at the very least to perform in a non-stationary fashion. And then ultimately, there's a speed limit that even if we ignore all the biology and the hardware, our signals only persist for so long. Remember, we're measuring them in time. And so if the signal lasted a week, it would be great. We could spend a lot of time sampling that signal, but it doesn't. It lasts maybe 30, 40, 50 milliseconds. And there are only really two variables that are relevant when we define that time. One is that the biological structure, which is presumably constant. That's not something you're going to manipulate on your subjects. And the magnetic field strength that you're operating at, B0. So this is 3 Tesla. Now, if you've bought a 3 Tesla scanner, that's also a fixed variable. So this situation is now completely fixed by virtue of your subject and the scanner that you've purchased. So this is ultimately the speed limit. There's no point in sampling for any longer than your signal stays around. You might as well start again and generate some new signal. Yeah. Go ahead.
Let's say that I'm not doing an experiment, but I'm reading an article about someone who did fMRI with animals. And he doesn't have this medical restriction of doing this UVDT, or he wants to go faster. So is it possible to do it on a machine? And if so, it probably can affect the results. So as a reader, should I ask about it?
Well, so most of the animal fMRI is done on non-clinical machines, right? And then there you worry about the speed of the hardware. So you tend to have everything tends to be about 2 to 5-fold faster than you can do in clinical. So the receiver is faster. You have higher bit depth in your receiver. The gradients tend to be maybe even an order of magnitude larger. So you can do an awful lot more with the animal systems. So in that case, and also they also tend to operate at higher magnetic fields. You'll see 4.7 to 17, 20 Tesla machines. So very often the signals will persist for an awful long time. So they can do things that are at a very different physical realm than we can do in humans. As far as stimulation effects are concerned, I don't really know if there's a big concern in animals because most of the time they're anesthetized. If you were trying to do awake animals and you were just immobilizing them with drugs, then yeah, that might be a concern because they might well be feeling some sensations. But I'm not familiar with those restrictions. It'd be interesting to find out. Okay, so let's look quickly at the concept of the default. So this is very much aimed at people who have scanned or are getting ready to scan, and you're going to want to start to think about what it is that you're going to do on the SCIRA. What's this default going to look like? How fast can you go? How small can the voxels be? You might as well leave now if you want 100 micron resolution and millisecond temporal precision. We're a couple of orders of magnitude beyond that right now. But let's look at what we can get. We're going to drive the scanner to its limit. It goes to 100. We're going to drive it to 100. You have a maintenance contract, I assume, so if something blows up, you can have Siemens come in and fix it. We do have some biological constraints, again, on the sampling, because we're looking at plumbing, not electrical activity. So we're going to be looking at the vascular effects of brain activity. And so we've got this hemodynamic response function, this function that's going to take 5 or 6 seconds to change in response to, let's say, an audio stimulus or a visual stimulus. And that's going to define a Nyquist condition for sampling that function. We're going to need to sample that at a frequency of about twice the rate of the vascular changes. Rich Ivory isn't here, so I can ignore the cerebellum. Anyone who does motor, I apologize. Apparently the cerebellum is a part of the brain. Certainly the cognitive neuroscience people, actually they're just starting to get interested in the cerebellum again, because they suddenly realize that they can build these networks that go into the cerebellum as well. In any case, until fairly recently, I would say probably the last couple of years, most people were going for full cortical coverage and pretty much ignoring the cerebellum. But that's maybe okay as a default position. Just bear in mind that I'm going to aim for the cortical coverage, and if you're very interested in cerebellum as well, then you're already going to need to depart from the default that I'm going to show you here. So there's the hemodynamic response function. It should look familiar to most of you. There's the time on the y-axis. And you see this is in response to visual cortex, so it's some sort of flashing checkerboard, etc. And you see a peak in the blood flow changes, the blood flow driven changes, after about 4 to 6 seconds. That number has a lot of slop in it. So if we were defining, if this was an electrical signal, and we knew it was exactly at 5.2 seconds every time, then we could define exactly the Nyquist condition for sampling this properly. But we don't know that. And the vasculature is variable. And so if the vasculature that's changing is very close to the neurons, you could have an earlier response. It might peak as early as 4 seconds. If you're looking at a draining vein, it might be peaking as late as 6 seconds. So we're going to have to be conservative. I know that there are people who do event-related fMRI with 3-second temporal sampling. I think that's on the hairy edge. I think you need to be 2.5 seconds or faster. Or you may start to weight too much towards the large draining veins and actually lose an awful lot of the really useful signal, which is much farther upstream, that's in the small venules and the microvasculature. We have yet to even breed undergraduates with no scalp fat. So unfortunately, your test subjects will have this annoyance. That means that one of the restrictions on any kind of brain imaging that we do is to eliminate the scalp signal. This is going to be a contaminant that is essential to eliminate. There's our Nyquist condition. We're going to aim for about 2 seconds because I think that that's a fairer thing to do. And we can get as much resolution as we can, but we're going to recognize that pretty much most of neuroscience is looking at Brodmann's areas that once you get beyond about 7, 8, 10 millimeters in length, you're going to lose an awful lot of precision. You're going to start to blur functional areas together. So that's going to be our loose specification for the size of the voxels. And then we'll see if we can get much below that. Okay? The last requirement is another requirement that's set by virtue of the biology and the field strength that you're operating at. This is a manifestation of the duration of the signals. So basically, the T2 star is the time constant that tells you how long the signals persist. So T2 star would typically be about 25 to 30 milliseconds, and it's an exponential decay. So by about 3 T2s, by 60 to 80 milliseconds, all your signals gone away. All the useful signals gone away. But for bold contrast, to get the maximum functional contrast, we actually want to set our echo time, which I'll talk about in a sec. We want to set this echo time, which is the center frequency in K-space. We want to set that to be approximately equal to T2. Now, that doesn't have to be exactly T2. There's a lot of slop, and I think I've got a slide on that this afternoon for the more advanced talk. But that's our loose operating criteria. We don't want to be at 10 milliseconds TE. That would be too short. And we don't want to be at 50, 60, 70 milliseconds TE. That's going to be too long. There's not going to be any signal left. Yeah.
If we use block design, 10 seconds simulation and 10 seconds rest, can't we use slower LTR, 4 seconds, 5 seconds?
Yeah, you could, but so most people these days do event-related block designs. So you'd still want the temporal precision, even though. So you're doing temporal precision. Your event-related stuff gives you the temporal precision with jittering, and then the block design's giving you power, right? So that's what most people do. I don't know that there's many people doing block designs exclusively just with 8 hertz flashing checkerboard for 20 seconds, except physicists. Physicists do that all the time. That's all we know how to do. So yeah, you could definitely for block designs. You could do significantly slower. Again, I wouldn't go much slower because you're going to lose statistical power. The more samples you can get, the better, right? Well, no, even then, you see. So that's the thing. So this is where, MRI slightly differs from Nyquist. So having more samples on these waveforms actually helps. So this is something that is a very in vogue topic at the moment. If you go to the brain imaging conferences this year, I'm sure it's going to be the hot topic, is exactly what temporal resolution is useful for in fMRI, right? Because everybody knows it's very sluggish. There have been some classic experiments that show that if you show two brief visual stimuli together, maybe separated by 100 milliseconds, you can resolve those in shifts in the time to peak. Right? So we know that there is intrinsic useful temporal information by going faster. And now the question is, now everybody's doing these, as we'll see this afternoon, now everybody's doing these very, very rapid whole brain scans in a fraction of a second. The question is, how do you interpret what you see? You know, how does it, especially if you're doing a resting state scan rather than something that's driven by a stimulus. So you really don't know anything about the system that you're measuring. You have no independent verification, no independent variable. You just have these signals coming back out. So that would be very interesting. So, but in any case, the one thing that we have shown, or people have shown, is that having more samples is just good for statistics. So it gives you statistics.
Well, what is the bandwidth of the signal?
The
original signal,
of the fMRI signal. Yeah. We would typically sample in the time in the readout domain. If I zoom back, well, if you remember the green, on one axis, on the green axis, which is X, about 100 kilohertz. On the Y-axis, only about 2 kilohertz. There's a big mismatch. So for those people who know about such things, that's why this axis, the phase encode axis. Yeah, right. And that has a profound effect as when we start showing, for those of you who have not looked at EPI before, when you look at EPI, one direction is perfect, the other direction is distorted. It's distorted because we have a very low bandwidth in this direction. It would be lovely if we had high bandwidth in both, but we don't. That's one of the artifacts that we pick up from having speed. Right? By building that up, we get intrinsically low bandwidth. The sampling from line to line is about every half a millisecond. In fact, I can show you here. So, so here's. I'll just orient you to the answer to that question first. So the sampling, the data acquisition is happening under these periods here, these green periods. So I'm not showing signals, this is just showing the actual readout. And so each one of these green episodes is about 64 data points acquired in about half a millisecond. So you can quickly work out what that, 1 over that number is the bandwidth. So it's in the tens of kilohertz range. However, the time between these little tiny red triangles is about half a millisecond. So that defines a 2000 hertz bandwidth. So this is a very slow domain. So we have rapid information being detected under the green boxes, and we have very slow evolution or detection of spatial information in this red axis. So this is one spatial axis in the image. This is the other spatial axis in the image. So it's the same pulse sequence that I showed you earlier. The reason I'm showing you this is just in case anybody is interested in looking at what is in an EPI sequence. This is the standard EP2D sequence that's on the Siemens machine. In no particular order. So this is the FAT-SAT module. This is the crushing module. So this excitation pulse, which we don't care about particularly, it's just it takes time. And these gradient episodes collectively take about 15 milliseconds. And that's what needs to happen for each individual slice in order to make sure that you don't get signal from the scalp fat in your subject. If you do, then you get contamination in your fMRI. And that's really a shame because this is a really large overhead. So the whole EPI echo train probably only takes 40 milliseconds, and here's 15 milliseconds just simply preparing each slice. It's just one of the costs of doing business. These little fellows here I'm not going to go into. This is just some crushing gradients for those of you who care about such things. This is just what cleans up the signal from the previous slice so that none of the signals that do survive from the previous slice can contaminate this current slice. Oops. This is the slice selection. So this is the excitation part. This is what defines each slab. So this will change very slightly from slice to slice as we go down through the brain. And this part of the sequence in green is basically the same throughout the rest of the sequence. Something else that doesn't get much play in the literature, I think there's battery will be dying on this. I'll just use the cursor. So something else that doesn't get much play in the literature is these three little guys here. These are the Nyquist ghost correction echoes. So this is also about a 1.5 millisecond overhead. It's not terrible. But this is an essential step to clean up a lot of the artifacts that would otherwise contaminate each of your EPI scans. So this is an essential little step. I just mention that for completeness, just in case you're wondering why. If you ever hear people talking about the Nyquist ghosts getting too high or the N over 2 ghosts getting too high, I won't bother getting into these terms right now, but just know that it could be because you're trying to correct an echo train that's 64 echoes long. That green train goes right through the wall out to the next room. You're trying to correct everything that's wrong with that green echo train with these three little guys in yellow right here. And just sometimes you just don't have enough information to correct something that's moving very slowly in the image domain. Right. So, and there's the workhorse. That's the part we're really interested in. So this is the part. This is dead. I'll use this again. This is the part of the sequence that most people in the last 20 years have focused on to speed the acquisition for brain imaging. So there's not so much we can do about this fact. This is just based a property of the chemistry of the sample. There's limited scope for changing any of that. It's from here on that we can really start to do some work and potentially start to accelerate the scans so that we can go faster than our defaults. That's what we'll talk about this afternoon. This is just a list of parameters that those of you who know about such things might recognize. This is the sampling rate that you're going to establish, 2,000 to 3,000 millisecond sampling rate. This is the repetition time. This is the time between shots at each point in the brain. And here's our echo time. I'm not going to go into that. This is a default range. So by establishing these time limits, this establishes a spatial limit of about 2.8 to 3.5 millimeters if you're trying to get whole cortical coverage. So if you need 1 millimeter precision, that means either you need a new method if you're going to do whole brain, or you need to restrict your coverage to a small chunk of the brain. You can't do the whole cortex, right? Something has to give. This is for Adi as much as anyone who's scanned on a Siemens before. There are certain restrictions as well as the ultimate restrictions in speed. There are also some effectively hardware bugs built into these scanners, and we need to make sure that we don't collide with one of those. So this is a problem on the Trio scanner that I have. I don't know what it's like on the Skyra. I think the Skyra is actually free of mechanical resonances because I think Siemens learnt their lesson that they shouldn't send scanners out where you could basically run the thing badly. So I think your scanner is going to be pretty clean. Zoom through those. So this is what my center uses as their starting point. So this is what people look at when they start thinking about their fMRI experiment, and then from there they decide whether any of their key specifications is not met in this list here. So we're going to be sampling at 2,000 milliseconds. The echo time is a little bit shorter than the range that I specified. It really doesn't play. It doesn't cause any limitations for the detection of functional activation, but it does. By going as short as possible, we save a little bit of time. It means we can cover a few more slices of brain in our 2,000 milliseconds, because that's all we've got to use per shot through the brain. That corresponds to about 3 millimeter voxels. Echo spacing we don't care about. I'll skip over that for now because it's just a hardware limitation. The slice thickness is comparable to the voxels. Most people like to be able to resample their brains, so they like to be able to operate with relatively isotropic voxels. And so 3 to 3.5 milliseconds millimeter slices with 30 to 36 contiguous slices will cover pretty much all of the cortex except for the largest heads. Now you might have to play some games with tilting the slices at the right angle to get the coverage of temporal lobes, etc. But by and large, that will get you about 110 millimeters of coverage, which will cover most of a normal person's brain. You do need to bear in mind, though, that larger heads could very easily fall outside of that range. So that's one of the criteria that you need to think about. If you're doing kids, it's not a problem. If you're doing adults and you are unsure about the largest brains, you need to start thinking a little bit more about coverage. I'm going to come back to this interleaving versus contiguous issue in a later slide, I think again this afternoon. This is just another experimental issue that is a quick way to clean up or make your experiments slightly more robust. So we always use contiguous slices, either descending or ascending. We never use interleaved slices. Again, a physics point for anyone who's in the audience who understands anything about slice selection. The slices that we select are actually slightly trapezoidal. They're not perfectly square in profile, which means we need a slight gap between them to stop them from coalescing on top of each other. In Siemens language, that corresponds to this gap parameter. So this is a percentage of the slice thickness. Zero gap, it doesn't actually correspond to really zero gap, but it's not actually necessary. So 5 or 10% gap is about what you need to define effectively contiguous slices in your slicing direction. So this is just a practical point. It's possible to go up to 20% gap without skipping over any brain, so there's a little bit of slop in the shape of those trapezoids. But again, this is something you can just fix and then not worry about. Okay.
Excuse me?
Yeah.
All these recommendations are specific or more general? Because there are people who are not from here.
Okay. Oh, let me go back a step then. I didn't realize there'd be GE people here. Fabulous. It's a shame Gary Glover isn't here. Okay. So here's a question. So why EPI, right? If you were at Stanford, oops, I got overshot. If you were at Stanford, then you'd be using spiral scanning for fMRI. And that's partly because Gary Glover is one of the team that invented it, and partly because he's absolutely convinced that it's the best way to cover the brain. So in GE, you have a few differences, but you have more similarities than differences. So one of the things that some GE sites use this Gary Glover's spiral sequence. Most people don't use spiral for very prosaic reasons. One is that EPI is ubiquitous. It comes on every single scanner. Spiral has to be installed specially by somebody like Gary Glover. So even Siemens doesn't provide it. So you've got to go buy it. Secondly, people tend to experience inertia. So the place that you do your graduate training tends to dictate what you then like from then on. So if you were a GE person, chances are you'll favor GE from then on. Not necessarily, but it tends to be the case, at least until you reach the academic ranks. So postdocs and graduate students certainly tend to be biased towards their prior experiences, a bit like Mac and PC. It just depends on your preference. There are some practical issues, though. There's an additional processing step that's required before you can use the Fourier transform. You need to regrid a spiral of K-space, which you see over here on this diagram. This has to be turned into something that looks rectilinear, and then you can apply your two-dimensional Fourier transform. So you've got all these various wiggly gradients going on. There are some issues with driving the hardware with wiggly gradients rather than trapezoidal gradients. That's a hardware restriction. But really, when it comes right down to it, it's a little bit like the old joke about academic politics. You know, the reason why academics fight so vociferously is because the stakes are so small. It's the same thing here. You could argue, you know, if Gary Glover was here, he and I could argue about this for, till dinner time. From your perspective, the differences and the benefits are second or third order. So most people just don't even bother to think about spiral. It's not like it's another domain. It's not like some magical part of the universe where everything is clover. There are some things that are better. There are some things that are worse with spiral. So as far as the similarities are concerned, let's go back to the sequence. So for GE users, this part here is the same. So you do navigator echoes basically the same, and you do the readout basically the same. The only thing that differs substantially is instead of doing this fat suppression and then and then slice selection separately, these are combined by default in GE. You don't have to do that, but that's just the default. So this is it's known as water excite, or it's a spatial spectral pulse, depending on your lingo. Again, there are pros and cons to that. The pro is that it's faster, so it saves you a bit of time. The con is that the effective slice thickness is wider. So you can't get below about 2.5 to 3 millimeter slices. They're more like 4 millimeters, and they tend to be quite flat trapezoids. So that tends to give up a lot of precision. There are some other differences that I probably won't go into, but feel free to ask me GE-specific questions. But as far as the raw parameters are concerned, let's go back forward. It is. If you went to most GE shops, you could achieve within 10%, plus or minus, all of these numbers. Because the physical restrictions and the biological restrictions are exactly the same, right? There's no magic formula. The biggest differences really are operational. They're in the software. There's very little difference between the platforms in terms of physics. Now there are some, if you guys want to talk later about, if anyone's interested in Philips versus GE versus Siemens, things like that, there are some trade-offs that the manufacturers play because they're trying to satisfy a particular market. So you don't necessarily have the same style of scanner purely because GE has their installed base and they have certain desires, and then Siemens has theirs and they have certain desires, etc. So there are differences that do tend to get reflected in the product, which we can talk about. But again, within 10%, it's not going to be a big deal. And I would still argue that what's more important is that you have a default position. You have a well-characterized protocol that you understand fully. You understand all of the problems that can arise with it. Okay, so let's see how far we're getting. Right, we'll press on for another 10 or 15 minutes, see how we get. Maybe we'll take a break. Okay, so that was the specification. That's what you've got today. So the question then is, why can't we go faster? Why don't clever people invent faster methods, better gradients, whatever we need? Why? Well, this is an interesting observation, actually. If you look at those parameters, the actual performance of the scanner today is arguably not radically dissimilar from what it was 10 years ago. So the first 3Ts came out around 2002, 2003. Siemens had an Allegra head-only scanner. Because it was a head-only scanner, by the way, it didn't have gradients that covered the heart, so they didn't have to worry about cardiac stimulation as much. They could actually drive their gradients faster. So in 2003, you could buy a scanner that was intrinsically faster than the scanners that you can buy today. That's an interesting observation. We've taken a step back in many ways. Anyone interested why? Why is it? That was a rhetorical question. Why can you not buy a head-only scanner that's faster than the current scanners you can buy? I'll give you a clue. The market for research scanners is the market for clinical scanners worldwide is huge. They sell thousands of these things a year to hospitals. Radiology is a big deal. That's what drives it. It's sheer luck that we can do our research on what is essentially a clinical machine. This is not a scientific instrument, right? You're buying a machine that can be put into a hospital and used clinically. You're driving it as a scientific machine. Make sure you always keep in mind, every now and again, remind yourself, this is not a scientific instrument. It wasn't designed to do fMRI. It's just sheer luck that it does it. Okay.
What's the intrinsic resolution that you can't really go beyond? By the physics of fMRI.
Physics of fMRI or MRI?
MRI.
Different question. So the physics of MRI is about 4 microns, and that is a limit that's defined by the mean free path of diffusion of water. If the spin moves during its frequency encoding, it accumulates enough phase that you can't then tell where it is. So that's the intrinsic limit. Right. And fMRI is really limited by the plumbing. So fMRI is limited by your sample. So the problem is that we're looking at these vascular changes that are millimeters to centimeters from the sites of activation. And so even if you increase the spatial resolution of your image, you don't necessarily get new information. Yes.
So money is really
Money? Yes. That's right. That's exactly right. So this is a problem. So this is one of my bugbears. So there's another thing for you guys to ponder in bed at night. You can buy a 1.5T scanner. You can buy a 3T scanner. And you can buy a 7T scanner. That makes a sort of mathematical sense, kind of powers of 2. But why can't you buy a 5T scanner? Why did nobody park a 5T scanner in the middle? Why do you need to spend... Oh, by the way, in fMRI or an MRI, it's about $1 million US per Tesla. So you're looking at $3 million for a 3 Tesla scanner, give or take. It's 7. It's actually more like $8 million now because the European Union's not doing so well. So the euro's got weak. But it's about $8 million just to buy a 7 Tesla scanner. That's without any site prep. You're looking at probably another 3 or 4 million to install the thing. So that's a lot of money. And 7 Tesla scanners don't do whole brain imaging very well. So you would think that there would be some scientific halfway house between 3T and 7T. That's naturally a domain operated by scientific instrument companies. But you'll notice we're talking about GE, Philips, and Siemens. They're not scientific instrument companies. They're medical companies. They sell medical devices. By them selling 7 Tesla scanners, they drove out Varian, Bruker, who else? There were a couple of other people who were making custom scanners. But they took the market away from the scientific instrument side. So until we as a community can convince Siemens, GE, etc., that there's a reason they should be building faster head-only scanners that do fMRI as well as it can be done, we're going to be limited by what we can buy for clinical work. So really, yes, it's a money-limited operation that we have right now. So that's very depressing, wasn't it? Right, let's liven things up a bit. So can we drive the gradients harder? Well, we could if we did a couple of things. We could either use a head-only scanner. That's a great thing to do. So if you're talking to Siemens and you want to drop some ideas in their ear, that's a great thing. They should probably revive that program and build a head-only scanner. By the way, the Human Connectome project, the Massachusetts General Hospital part of that project, they built their own effectively head-only scanner. It's an insert scanner, head-only gradient set. It's an insert gradient set that goes into their 3 Tesla scanner. And they did it exactly for all of the reasons I've been talking about. It means they can drive it harder, make the gradients get bigger. They built themselves a scientific instrument. Okay. Another way we could do it, which nobody's tried yet, so if anyone's got an interest in this, you could possibly make yourself a nice side company, is to simply shield the heart. So you create some electromagnetic fields. Okay, well, fine. We'll just put some copper mesh or something over the body because we don't care about the body. We're only interested in this part here, up. Everything else is just life support system. So it's somewhat useful, but also gets in the way for fMRI. And so if that's the case, why don't we just simply, again, treat it like a scientific instrument and fix the problem, okay? So this is something nobody's worked on. If you're doing it for use in research, you would need to have all of the safety interface so that it could always fail safe, etc. So it's not trivial, but nobody seems to be tackling it in that fashion right now. So we're left with this domain, or these 2 domains. Maybe we can go faster in our sampling of that 2-dimensional K-space plane. Maybe we can skip some information. Maybe we can somehow speed things up. If we do, and we can use methods such as Grappa or on a GE Sense, then we might be able to get 20 to 40% more slices in our repetition time. So we might cover, we might get down to the full cerebellum as well as the cortex in 2 seconds. But this isn't going to, again, this isn't going to open up some new doorway into the universe. We're not going to suddenly see an order of magnitude speed improvement. This is an incremental change. We can also do this thing called partial Fourier encoding, which I'm going to talk about a lot in a little while, where we can skip over some of the redundant information that's in the K-space plane. I'm just going to illustrate that for you in a second. There are, of course, some caveats to that. And this is where I want you to start to be thinking about the methods that you see today, and when you see them in the literature, is to ask what you give up. Okay, you get some speed or you get some resolution, and the cost is where? Right, there's always a cost. Is it hidden? Is it a money cost, or is it an experimental cost? Is it a performance cost that comes somewhere else in your experiment? The last thing, this is the new sexy stuff which I'm going to talk about this afternoon. And this really does almost open up a new dimension in the universe. So far, I'll tell you the good news. The good news is it looks really amazing on my scanner. The bad news is I don't know why. It shouldn't. And it's really quite perplexing, but it's close to an order of magnitude improvement, and it's pretty awesome to see. So for those of you who've done fMRI before, you might be pretty excited to see that. So here's back to our K-space plane. So I'm just going to skip forward 1 slide for a sec. It turns out that we have a lot of redundant information in this 2-dimensional representation. This conjugate symmetry property basically means that all the information that's in the top half of this K-space is reflected in the bottom half in a perfect situation. So if we only were able to detect half of this, we could simply use the mathematical properties that we understand to recreate the missing half. So in principle, we could simply not acquire the first or the second half of the k-space. So that would mean we could just simply stop sampling right about here, and then we could reconstruct all of the signals from what we've already acquired, and we've just saved 50% in time. That seems pretty cool. Practically, however, because we live in this imperfect world, not a perfect mathematical world, practically, however, there are differences between the signals in the top part and the signals in the bottom part. There's enough differences that we can't just simply recreate the signals. We need a little bit more information. So what we do is we go just over halfway. In this case, we've got 3/4 of the k-space plane sampled. And then what we can do is recreate from the top part, we can recreate the bottom part and save some time. That's represented just simply here. So we're going to simply use these mathematical tricks to reconstruct the missing information. Now, in doing that, there is, as I mentioned, a caveat. There are really two caveats. The first, well, this is not fMRI, by the way, and I picked this intentionally because if I showed you an EPI scan, you would see the asymmetry too strongly. This is actually a fast spin echo scan. This is a clinical scan, anatomical scan. And even if you Fourier transform that, or the inverse Fourier transform it, and see the k-space, you'll notice that there's a degree of symmetry, but it's far from perfect. You've got some signals in the bottom here that are not perfectly represented in the top. So if I chop off the bottom 1/4 of the echoes, I'm going to lose information that I cannot recover mathematically from anything that I do at the top. So by omitting these echoes, I cannot possibly get to the exact situation that I would have if I did the whole of k-space. So that's one of my costs. I'm going to give up something, right? In fMRI, it's going to turn out to be signal in orbital frontal cortex and temporal lobes, the two toughest areas of the brain to image. So there will be a cost there. The other cost, which I'm not going to go into, is that on the Siemens, I'm not sure how GE does it. They call it something different, but on the Siemens, they just simply what we call zero fill this matrix. They just add zeros. They just complete the grid of 64 by 64 data points by putting null values 0, 0, 0, 0 throughout, and then they do the Fourier transform. That has there's a little bit of apodization that happens for this edge, so it's not a hard edge. Those operations combined tend to smooth the voxels slightly. So your nominal resolution might be 3 millimeters, but your actual effective resolution is going to be more like 3.5 or maybe even 4 millimeters. That's something just to bear in mind. So most of you who are doing fMRI smooth anyway in post-processing, perhaps 5 or 6 millimeter Gaussian kernels. So in general, it's not a big deal. The modest amount of smoothing isn't a showstopper. The bigger deal tends to be the signal loss from not sampling the full k-space plane.
Just small filter.
Yeah.
So it is different windows on the square. All sorts of ways.
Right. So this is a filter, but this is a filter that we're going to apply during the acquisition. So it's going to be fixed. Once you've got it, you've got it. Right? It's embedded into the acquisition. Afterwards, you can do anything you like. Right. So typically, certainly on Siemens tends to use more filtering in line GE uses inline filtering. Siemens does not. Siemens doesn't do any filtering in the k-space domain before FT by default. GE applies a Fermi filter, a circular filter, by default. And as far as I know, there's no way to turn that off. So you will always see a slight difference in smoothness between GE and Siemens. Yeah. That was a big deal for multi-center trials a couple of years back, 4 or 5 years back. So, okay. Again, this one particularly aimed at Leon because I know Leon's interested in the temporal lobe. It's a challenging area to image. First of all, if you look just at the parietal and occipital cortex, in these top 15 slices, you'd be hard pushed to see any differences between the full Fourier, so this is acquired with the whole k-space plane, and this in this case where we just simply neglected to acquire the last quarter of the echoes. In Siemens parlance, they call this 6/8 partial Fourier, but 3/4, whatever you want to call it. It means leaving out the last 1/4 of the echoes. And there's really no difference in the superior slices. It's not until you get quite deep in the brain that you start to see regions that have enhanced dropout. So you're definitely going to see some progressive signal loss in the temporal lobes, maybe a little bit in the OFC as well, just depending on the shape of the head, etc. And there are some tactics, which I'm going to come back to later on, where you can control somewhat exactly where these dropouts arise. Let me just see where I am. Okay. Let's go on. Should we carry on and then break for lunch? I've got about 20 minutes. Yeah. Just zoom through this. And then you guys can ask questions too.